right. Geometry lesson 38, talking about perpendicular and angle bisectors of triangles. So we're still back into triangles, and we're going to be talking about some lines that play with those. Bisectors. What is the term, before we get into what all the nodes say, what does a bisector do? Cuts. Yeah, that's true. Let's be a little bit more specific. Two equal halves. Very good. So putting all that together, an angle bisector is going to divide an angle into two equal halves, or in this case, two equal angles. Okay? Right, two congruent angles. So an angle bisector is going to take one larger angle and split it into two equal angles. All right? When all three angles of a triangle are bisected, and we have those lines coming through that triangle, we call that the incenter of a triangle. So far, we've covered two things where we're drawing lines through a triangle and we're looking at where they all connect. The first one was the circumcenter, which we covered some questions in our homework today over circumcenters, where we have 1/3 and 2/3 being broken down, or centroid, I'm sorry, centroid. And then we've had orthocenters, where we're talking about perpendicular, lines being drawn and those things coming together. Today we're going to talk about incenters, and I believe circumcenters are going to come up as well. The incenter of a triangle is equidistant from all the sides of the triangle. And hopefully this will make a little bit of sense when we see it drawn out visually. But the incenter of a triangle is the same distance, that point where they could connect is the same distance from all of the sides of that triangle. In addition to finding the incenter of a triangle, angle bisectors can also be used to find the lengths of segments in the triangle. When an angle bisector intersects the side of a triangle, it makes proportional relationships given by what we're going to find in Theorem 38-1, which looks a little bit like this. And we've just drawn a line all the way through this triangle that has bisected angle M and created angles NMO and PMO, which are congruent angles. So if a line bisects an angle of a triangle, then it's going to divide the opposite side proportionally to the other two sides of the triangle. So it says PM, that's this side right here, over PO, that side right there, is going to be equal or proportional to NM over NO. Okay, do we understand that? Okay, so basically we're saying of one side of that triangle after it's been bisected, long side over short side is equal to, on the other side, long side over short side. Does that make sense? Right, and we can set up those proportions and solve for segments of that triangle. Okay. A perpendicular bisector, this is where we're talking about circumcenters. A perpendicular bisector divides a line segment into two congruent segments and is perpendicular to the segment. So I've tried to draw this so that it made maybe even a little bit more sense than just looking at the picture that you find on page 245 around the middle of the page. Right? Do you see that in your book or ebook? Okay. So we're looking at just the red line here. So granted, my lines aren't perfect. It was the best I could do just making this kind of by hand. All right, but this red line is supposed to be the midpoint, so it's bisector, perpendicular bisector. So the first thing that we would find in order to before I even drew this line, is I would need to find the midpoint of XY. Does that make sense? Once I found the midpoint of XY, I would have to, if I'm going through all of the math, I would have to know the slope of XY to begin to draw a perpendicular line from the midpoint. You see how this gets fairly complicated if I had to do all of this by scratch. Okay? Once I know the slope of XY, if I want to start to draw that red line that you see that's perpendicular, I would have to use an opposite reciprocal slope. Right? And then I could begin to draw that line off of it. Right? I'm going to draw that line through there. And I'm going to do the same thing to line YZ. I'm going to find the midpoint of line YZ, make a point where I would begin that blue line, find the slope of YZ, then use the opposite reciprocal to start drawing that blue line. Okay? Then I'm going to come down to XZ. Fortunately, it's a horizontal line. Horizontal and vertical lines are congruent. Okay, so I would find the midpoint, and I would just go straight up. Now, where the perpendicular lines cross, we call circumcenter. And the circumcenter of a triangle is equidistant from every vertex. So that's where I have those 4 tick marks, where I'm showing from P to Y is the same distance, from P to Z is the same distance from P to X. What you remember about incenters are equidistant from every side. Circumcenters are the same distance or equidistant from every vertex. That's the difference between an incenter and a circumcenter. Okay, is how they're equidistant and what they're equidistant to. Okay, so P is, PX, what you see, this purple line, is the same distance as P to Z as P to Y. Okay, so this picture took me a really long time to make because it's such a complicated figure to look at, and I wanted to make it in such a way that it made sense visually, enough that you could understand it. I don't know if I accomplished that, but in any case. So the circumcenter is not always inside a triangle. A right triangle circumcenter is on the hypotenuse, and an obtuse triangle circumcenter is outside the triangle. And I feel like we saw that whenever we looked at the orthocenter. Do you guys remember the orthocenter? Yeah, I got one person who remembers the orthocenter. Let's see, real quick. I want to take you back in your book to look at the orthocenter, but I got to remember what page it's on. Give me a second here. Page 206. Page 206. So really not terribly far away. And this would have been in lesson 32. If you looked at lesson 32, around page 206, it's the only difference between an orthocenter and a circumcenter is that a circumcenter is a perpendicular bisector of a side, whereas in an orthocenter, it's just a perpendicular line coming off of every side, going back to the opposite vertex. A circumcenter doesn't have the requirement to go back to the opposite vertex. Okay, so some of these terms can get really close to other terms, and they're terms that you're not necessarily used to. I would say probably before this class, none of you had ever heard of an orthocenter, a circumcenter, an incenter, a centroid, right? Had you ever heard of any of those things? So all these are brand new terms to you. This is where I would say writing some of these things down. If I'm sitting in the class, I'm not only going to write down the definitions of those things, but I'm going to underline the important parts of each of those definitions so that I understand the differences between those terms that seem so close to one another. Okay? All right. So you also see there on page 206 with that orthocenter where I have an obtuse triangle, that point of concurrency is outside the triangle in an obtuse triangle. The circumcenter lies at the center of the circle that contains the 3 vertices of the triangle. So any triangle that contains all the vertices, all the end points of a triangle is called a circumscribed circle. And we can do that with a lot of different figures, especially like whenever we see it in Algebra 3. If we're saying that a circle circumscribes even a square, we're talking about a circle that's outside, that's on the outside edges of a square, where the edges of that square or quadrilateral are on the edges of that circle. Does that make sense? So circumscribed means on the outside of a figure. Inscribed, which should make sense, means inside that figure. We could put a circle inside that triangle if we wanted to, right? So there's a difference between circumscribed and inscribed. So any triangle that contains all the vertices of a triangle is said to be a circumscribed triangle. Okay, that one shouldn't be too hard to see and understand. I think that's it for this. Hopefully I've got lesson 38 pulled up. This may not be, this doesn't look to be. Let me get into lesson 38. Let's hit pause for a second. All right. So this document was actually shared with you yesterday as part of lesson 37. This document contains questions from 37 and 38. All right. So notice that WY is an angle bisector because it divides XWZ into equal parts at XWY and YWZ. Does that part of it make sense? So what we want to remember is that this side over this segment is proportional to this side over this segment. Proportional meaning that we're taking those ratios, right? Blue over red equals blue over red. Okay, can we see that? I'm trying to think of different ways to visualize this so that we can kind of see what's going on. So as we go into this, the rest of this is really just dealt with labeling. So WZ is 10.9, ZY is what, 4? Okay, WX is 32.7. Okay, and we're missing that piece right there, right? So we're just setting up a proportion based upon that. Now, I'm going to tell you that this is possible, but I don't want you to get confused by it. I could do 10.9 over 32.7 and then set that equal to 4 over x. If I do blue over blue, then I'm going to do red over red, right? Or I could do 32.7 over 10.9 equals x over 4. I feel like if I do that, you're looking at too many different possibilities, and you run the risk of doing something wrong, like doing, let's say, 10.9 over 4 equals x over 32.7. That won't work, right? Doing things out of order. So for now, I'm going to go back to an original form here. One triangle over that same triangle in correspondence to the other triangle over its corresponding segment. Okay? So with that in mind, what am I going to write for my ratio here? Maddie? (32.7) over x. Okay, good. Equals? That's a 10.9 and this is a 4. 10.9 over 4. Very good. Okay? And if I want to solve that, I've got a proportion, so go ahead. Multiply. Okay, multiply 32.7 times 4. Do you have a calculator or anything that you can work with? Okay, just because I'm assuming you don't know that off the top of your head. That's not one that you necessarily should know. $130.8, okay, 130.8 equals what? 10.9 x, good. All right, so what's my last step that I want to do? By 30.8 divided by 10.9. Yeah, we're going to divide by 10.9 on both sides. All right, which should give us an answer for x. Does it come out evenly to just a flat 12? Okay. All right. Somebody want to check the answer key? Scroll on down to the bottom, look at number 1, see if our answer is 12 for xy. Huh? Chandler says yes. There. It's all in order. So this was question number 1. So 12. Okay. All right. So good job. All right. Let's look at number 2. All right. Let's see. We're going to go ahead and plug in our numbers. Let's see. It says find QR. So I'm going to go ahead and put an X where R is, right? We get that that's that length right there. Okay. PS. PS is 18. This length right there is PS. Ooh. Oh, in like, okay, so Michael's question is, what does PS stand for whenever you see somebody write a letter after they've sent their salutations, they wrote PS and then they said something else. PS stands for postscript, post meaning after, script meaning letter. So it's, you know, I went ahead and I ended my letter, but I forgot there was something else I wanted to say, so I wrote PS, postscript, da-da-da-da-da. Does that make sense? Okay. All right. So, not exactly what I was trying to get into here. RS is 18, and PQ. Oh. Okay. PS was it? I am tired. All right. That's my excuse anyway. 20. All right. Jordan, help me out here. What do I want to write? How do I want to set this up? 20 over x and 18 over 9. Okay. $180 should equal 18x, right? Okay. What do you want to do now? Divide by 18 on both sides. X equals 10. And one of the things that you could maybe see real quickly looking at this is 18 over 9 is equal to 1/2, right? You know, 1 over 2. So at that point, I could have substituted out the 18 over 9. I could reduce that fraction. So 20 times 2 is 40, right? Okay. Wait, oh no, I'm sorry. 18 over 9 is not 1/2. 18 over 9 is 2 over 1, right? Sorry about that. So 20 times 1 is 20, divided by 2 is 10, right? That makes sense. So if you can reduce the fraction, sometimes that makes the cross multiply and divide a little bit quicker. Okay. I believe we've already done 3 as part of the other lesson. Let's come down to number 8. Using this diagram, Katie, we want to find YZ. I'm going to go ahead and put an X there. Well, maybe not. We'll put something else in there because we're already using X. Let's say, give me a different letter, something that doesn't already show up there. B. Okay. We want to find B in this case. All right. Let's see, they tell me that XY is 2. They tell me that XW is 14. They tell me that ZW is 10. So Katie, help me write this up here. All right, so you're going a little bit different route here. 2 over B. Okay, good. So you're doing left segment over right segment equals full left side over full right side. Okay. All right. 14b equals 20. All right. Divide by 14. All right. Probably just going to get something similar to just a fraction there, right? 20 divided by 14. Well, what can I divide both those numbers by? 2, and I would get, I'd get 10 over 7, and that's probably going to be as far as I can reduce it because 7 is prime, right? So 10/7. Check the bottom, see if that's, it says 5/7. This should be number 8. Check out number 8. 1 3/7. Okay, so 7, just so we can get that, 7 would go into it 1 time, right? 1 with how many left over? 3, leaving me with 7 still in the denominator. So 1 3/7 would work. They didn't say how they wanted the answer, so 1 3/7, 10/7, or what, 1.42, something to that. Was that where it ended, or did it keep going on from there? Kept going, so yeah, I would go with one of those two answers over the decimal, because the decimal might be a bit irrational. 7 times 1 plus 3, yeah. Yep. All right. That's it. Don't have anything else for you. So I'm going to hit stop there. You guys can get to work. I know you guys didn't get your full 10 minutes, but hopefully in the